Chapter 8, Introduction to Hypothesis Testing, Part 2. I'll begin this video with the learning checks that pertain to the previous video, Part 1. Since that video ran a little long, I decided to begin this video with the learning check to assess our understanding of the material presented in Video 1. So let's consider this statement. A sports coach is investigating the impact of a new training method. In words, what would the null hypothesis state? So we learned that the null indicates that there is no change, no difference in after treatment. So again, it indicates that the treatment results would equal the untreated group. So let's consider these statements. The new training program produces different results from the existing one. The fact that it says, includes this word different, indicates to us that that is not a reflection of the null, because the null is saying everything is equal, things have not changed, there is no difference. The new training program produces results about like the existing one. Well, if it's saying that they're like the existing one, then it appears that it's indicating equality. So as we move through these statements, this one seems to be the most viable thus far, but let's go through the other ones as well. The new training program produces better results than the existing one. Again, the word better is illustrating that something is changing, right? In this case, it's improving. So that would not be an illustration of the null hypothesis. And then finally, there is no way to predict the results of the new training program. Well, we're engaging in hypothesis testing, so we are able to make predictions. Whether our predictions have supporting evidence is to be determined. So this one also would not be appropriate. Therefore, we see that B is accurate. The new training program produces results about like the existing one. So again, we see equality, that they're equal to one another. No difference, no change is being predicted in this particular statement. And again, that's reflective of the null hypothesis. Next, let's identify whether or not these statements are true or false. The first one, if the alpha level decreased, the size of the critical region decreases. Well, let's think of an example. Let's say alpha is equal to 5%. And if we decrease it to alpha equal to 1%, what does that happen to the critical region? Well, let's draw a distribution and partition off 95% in the center, right, which is reflective of 5% total across both tails, okay? And now if we decrease our alpha to 5%, what does that mean? Again, this area here is referred to as the critical region. The critical region is defined by the value of alpha. And so now if we decrease our alpha to 1%, what does that mean for the center area? Well, we're going from 95% to 99%. So this becomes wider. Agreed, right? Because now we're accounting for 99% of occurrences in the center. And what's left over is the 1%, right? We decrease from 5% to 1% alpha. Again, now this is the critical region. And hopefully I've drawn this well enough for you to recognize that if the alpha level decreased, in our example from 5 to 1, the critical region also decreases because the center area has increased. It's expanded to include 95% of all occurrences to now 99. So this area has widened, and as a result, the tails have decreased. The critical region has become smaller. Therefore, we would conclude that this is a true statement. The next one, the critical region defines unlikely values in the null hypothesis. If the null hypothesis is true. And this is correct. The critical region, which is determined by our alpha level, is identifying or defining the values that are very unlikely if the null is true. Again, the center, we would fail to reject the null if our values fall in this white area. We get to reject if it falls in the tails in the black shaded area. But nonetheless, what we're saying is that these values in the critical region, these critical regions, are considered unlikely if the null is true. Now again, I've stated before, these occurrences are part of the distribution, but they are small in frequency, right? So they are very unlikely if the null is true. And again, the null is stating that nothing is happening. There's no change, no difference. So if we do find a value that falls into the tail, again, we have support for the hypothesis that says that something is happening, the treatment is effective, but we also recognize that there's a very small chance that the occurrence was due to chance and not due to treatment. And again, this is all relating to the type 1 error that we'll talk about soon enough in this chapter. But just a little preview, essentially our alpha level is equal to the percent of engaging in type 1 error. Type 1 error says that you reject the null in error. So you say something and nothing is happening when something, you say something is happening when something really is not happening. Let me repeat that. A type 1 error is when you say something is happening, some change has occurred, when it really has not. So again, that results from obtaining the sample mean in the critical region, but that critical region value was simply due to chance and not due to treatment. And we'll talk much more about this when we get to type 1, type 2 errors in this chapter. But nonetheless, at this point, we can conclude that this statement is true, that the critical region defines unlikely values if the null hypothesis is true. In part 1, we identified the 4 steps in hypothesis testing, and we discussed step 1, which is to state the hypotheses, which include the null, and that's denoted by H sub 0, and the research, or also referred to as the alternative hypothesis, which is denoted by H sub 1, and we discussed that the null is indicating that there's no change, no difference, and the research is indicating that there is a difference. Then we discussed step 2, which was to set the criteria for decision, and this refers to setting our alpha, and we discussed that the common values of alpha include 5% and 1% for our purposes. There are other alphas, but these are the most commonly used, especially in our text and our examples. And now we're going to discuss step 3, which is to collect and compute sample statistics. And we'll end with step 4 in this video, which refers to making a decision regarding the data that we've collected. So before we collect data from our sample, we must recognize that data always is collected after the hypotheses are stated. So again, we need to state our null and our research hypothesis before we engage in the collection of data. And the data always collected after establishing the criteria level. So we must set alpha, right, before we collect data. The sequence assures objectivity. Again, if we collect data and then state our hypothesis, you can see where that would not be objective because we've already seen what the data looks like and we have a sense as to whether or not our ideas about differences or changes do occur. So to be objective and ethical, we must first state our research and null hypothesis, identify the criteria by which we're going to test that hypothesis, and then collect the data to analyze and then draw our conclusions. Again, those 2 steps must occur before we start to collect data for our sample. So once we collect our data, we're going to compute our sample statistics, which not only include a z-score, but also the mean. So we're going to have to compute our mean, which is the sum of x over n, and that will give us the sample mean. Again, that's going to be the basis of comparison. If we're administering a treatment, we're going to compare it to the untreated population, and then that sample mean also serves as an illustration of what we would anticipate the treated population mean to look like. So we compute a sample statistic, which is the z-score, to show the exact position of the sample. And here's our equation. Z is equal to the sample mean minus the population mean divided by the standard error. So again, this is mean difference, and this is the standard error. Again, average difference between m and mu. And again, as we learned back in chapter 5, the z-score is identifying the exact location of a value in relation to the center value, the mean of a distribution. In other words, this equation can be expressed as z is the difference between the observed sample mean, again that's m, and the hypothesized population mean, mu, divided by the standard error of the mean, which is standard deviation of the population sub m. So again, by converting that sample mean into a z-score, we've standardized that value so that we can make comparisons and then also utilize the unit normal table to determine the probability of that sample mean occurring if the null hypothesis is true. The null says no difference, no change. And so if we have a value, a sample mean that has a very high probability, then that supports this idea that the null well, we have evidence to support that null, which is indicating that there's no treatment effect. If that sample mean has a very low probability, indicating that it's occurring out in the tails, then we have support for the research hypothesis that says something is happening. And we'll discuss again the verbiage that goes along with what we do if our sample mean falls into the tails versus congregated around the center of the distribution. And what I'm referring to is, do we reject the null or do we fail to reject the null? So I'll say more about that in a subsequent slide. In step 4, we make a decision or draw conclusions regarding the sample statistic that we calculated. And if the sample statistic or the z-score is located in the critical region, the null hypothesis is rejected. Now what I've drawn over here is applicable to if alpha were equal to 0.05 or 5%. And what I've drawn here is in the center is represented by a proportion of 0.950, which is the equivalent of 95% of the occurrences are going to be seen here in the center of the distribution. In 5% or 0.05, a proportion of 0.05 is representative of the critical region split over two tails. And if our sample mean falls in the center, we fail to reject the null. And if it falls in the critical region, we get to reject the null. So again, the null says the null is equivalent of no change, no difference. And just to be clear, we're talking about no change or no difference between the mu, right, in the center and the sample mean that we computed. So again, if our sample mean, we produce a sample mean that was here, right, it's in this region that's considered very common and reflective of no change, no difference, no effect of the treatment. Whereas if we had a sample mean either here or over here, then that's reflective that something has happened, that the mean, right, the value of the mean has changed or shifted from here to there, or on the positive side from the center all the way into the tail. And if the mean difference is large enough, if it's far enough from the center, then that's demonstrating that the hypothesis, the research hypothesis, is supported, that we have reason to believe that it was the treatment that produced this difference in the mean. And again, if there isn't a large mean difference, then we have reason to believe that the null is supported. And again, we failed to reject the null. The null says no change, no difference. And we are failing to reject that idea. Again, technically speaking, it's not appropriate to say we accept the null, and I will discuss why in the subsequent slide, as I indicated before. But for right now, you can just in your notes, and I highly recommend that you do this if it helps you, to write in parentheses, accept the idea that no change or no difference was reflected in this particular research. But again, technically speaking, the proper phrasing would be that we failed to reject the null. We failed to reject the idea that there was no difference or no change if it falls close to the mean. And when we fail to reject the null, again, let's say, for example, our mean was 80 and our sample mean was, let's say it's 85. Again, numerically speaking, they're different. But if we fail to reject the null, essentially what we're saying, and statistically speaking, we're saying that 85, I should write 85 first, 85 is equal to 80. There's no difference, statistically speaking, based on the probability of that value occurring. So again, even though we see a numeric difference, if we fail to reject the null, that numeric difference, in this case between 80 and 85, would be attributed to sampling error opposed to treatment. And again, statistically speaking, we would be concluding that the 80 value, the sample mean of 85, is no different or equal to the population mean of 80. And therefore, we say, really, there's no change, no treatment effect. Conversely, if we have a population mean of 80 and our sample mean after treatment, let's say, was 100, right? Numerically speaking, yes, there's a difference. And let's say that sample mean was placed or occurs out in the tail. Then what we're saying is 80 is not, is different numerically speaking, but also statistically speaking, they're not equal to one another, and in that case we would get to reject the null hypothesis. So we'll go through a lot of examples to make sure you understand these concepts. But here in this graph, the purpose is to illustrate a visual of what to do in terms of drawing conclusions and making your decision regarding the sample statistic that has been computed after you've collected data. Here's an analogy for hypothesis testing that may help you better understand the difference between the decision to reject the null or fail to reject the null. In short, failing to reject the null simply means that we conclude there isn't enough evidence to conclude that there is an effect or a difference between quasi-independent variable categories. So it may seem awkward to phrase both of the two possible decisions in terms of rejecting the null hypothesis. Either we reject the null or we fail to reject the null. These two decisions may be easier to understand if you think of a research study as an attempt to gather evidence to prove that a treatment works. From this perspective, the process of conducting a hypothesis test is similar to the process that takes place during a jury trial. For example, the test begins with a null hypothesis stating that there is no treatment effect. Similarly, a trial begins with a null hypothesis that the defendant did not commit a crime, innocent until proven guilty. The research study gathers evidence to show that the treatment actually does have an effect. Similarly, police gather evidence to show that the defendant really did commit a crime. Note that both are trying to refute the null hypothesis. Next, if there is enough evidence, the researcher gets to reject the null hypothesis and conclude that there really is a treatment effect. Similarly, if there is enough evidence, the jury rejects the hypothesis and concludes that the defendant is guilty of a crime. Finally, if there is not enough evidence, the researcher fails to reject the null hypothesis. Note that the researcher does not conclude that there is no treatment effect. They simply there simply is not enough evidence to conclude that there is an effect. Again, we just don't have enough evidence to say that there's an effect. And if we draw parallels to the jury trial, if there is not enough evidence, the jury fails to find the defendant guilty. Note that the jury does not conclude that the defendant is innocent, simply that there is not enough evidence for a guilty verdict. So hopefully this helps you better understand the verbiage necessary when we are drawing our conclusions. Again, the options are to reject the null. Ideally, that's what we hope for. We hope to find a sample mean that is very different from the hypothesized population mean, and we have support, therefore, for treatment effect or differences between a quasi-independent variable. If we fail to reject the null, again, all we are stating, the conclusion is that there simply wasn't enough evidence to conclude that there is an effect or difference between the quasi-independent variable groups. Hopefully that helps you better understand the difference between the two and why we use this awkward verbiage of failing to reject the null. Again, if it helps you, by all means, in your notes in parentheses, just write you accept the idea that nothing happened. That may help you better understand the concept, but just recognize that technically speaking, that we would never say we accept the null. We just fail to reject the null. So again, whatever it takes to help you master that concept, implement that in your notes, but be conscientious of the phrasing when it comes to real application of a hypothesis testing, and of course on homework examples and test items. And we'll end this lecture with a learning check. Decide if the following statements are true or false. When the z-score is quite extreme, it shows the null hypothesis is true. So again, let's visualize this. If we have our distribution mu, an extreme z-score means that it's occurring out in the tails, either on the positive or negative side. And we're stating it shows that the null hypothesis is true. The null says no change, no difference. So if our sample means are out here in the tails, then we are showing a change. And statistically speaking, it's probably a significant difference because of the probability of those values occurring. So this statement is false. When the z-score is quite extreme, it shows that the null hypothesis is not true, that we get to reject the null. We get to reject the idea that there is nothing happening, and we have support that something is happening, that there is a treatment effect or a difference between the quasi-independent variable groups that we are studying. Next, a decision to retain the null. A decision to retain the null means that we fail to reject the null. So if we fail to reject the null, that means you've proved that the treatment has no effect. Well, we just discussed this, right? If we fail to reject the null, we're simply concluding there isn't enough information or evidence to conclude that there is an effect. It does not mean that we have proved that there is no effect. We simply don't have enough evidence to show an effect or to support that there is an effect. So this statement would be considered false. And that concludes part 2 of chapter 8. In the next part, we'll be talking about the errors that may occur when engaging in hypothesis testing, type 1 error and type 2 error.